There is a simple assumption we make about planets and temperature. The closer a planet is to its star, the hotter it should be. The farther away it is, the cooler it becomes. This relationship is so intuitive that it's rarely questioned. Distance determines how much energy a planet receives, and energy determines temperature. In most cases, this rule works remarkably well. Mercury is close to the Sun, and it gets extremely hot. Mars is farther away, and it's much colder. Gas giants orbiting at great distances are cold worlds, bathed in weak sunlight. Temperature, in this view, is a simple balance. How much energy comes in? How much energy escapes back into space? If more heat enters than leaves, a planet warms. If more heat leaves than enters, it cools. This balance explains why planets settle into relatively stable temperature ranges over long periods of time. It's predictable, measurable, reliable. Which is why this planet is such a problem. Based on its distance from its star, it should not be as hot as it is. Not even close. Its orbit places it well outside the region where extreme surface temperatures would normally be expected. It does receive strong sunlight, but not enough to explain what we observe. And yet, this planet is hotter than any other in the solar system. Hotter than worlds that orbit much closer to the Sun. Hotter than planets that receive significantly more direct energy. This immediately raises a red flag, because if distance alone can't explain the temperature, then something else must be happening. Something inside the planet's system. Scientists began by checking the obvious explanations. Measurement errors, instrument limitations, incorrect assumptions about reflectivity or surface composition. But the data was consistent. No matter how it was measured, the result was the same. The planet retained far more heat than it should have been able to. That means energy was entering the system, but not leaving at the expected rate. In other words, the planet wasn't just receiving heat, it was trapping it. This shifts the question entirely. The problem is no longer how close the planet is to its star. The problem is what happens to the energy once it arrives. On most planets, excess heat eventually escapes. It radiates back into space, allowing temperatures to stabilize. On this planet, that release never happens efficiently. Heat builds, persists, and accumulates over time. This is not a small deviation from the expected model. It's a complete failure of the system to regulate itself, which tells us something important. The extreme temperature is not an accident. It's the result of a process that was set in motion long before the planet reached its current state. To understand why this planet became hotter than it ever should have, we have to stop looking at its distance and start looking at what surrounds it, because the heat isn't coming from where we expect. It's staying because it has nowhere to go. The heat on this planet doesn't come from a stronger star. It comes from a system that no longer lets energy escape. What surrounds this planet today is not a normal atmosphere. It is a dense, crushing remnant of what once existed, thick enough to fundamentally change how heat behaves. When sunlight reaches the surface, energy is absorbed quickly. But once that energy turns into heat, it struggles to leave. On most planets, heat rises and radiates back into space. It disperses. It escapes. The system stabilizes. On this planet, that release is blocked. The atmosphere acts like a thermal trap. Radiation enters easily, but outgoing heat is absorbed, re-emitted, and redirected back toward the surface. Instead of cooling down, the planet reheats itself. This process doesn't depend on day and night cycles. Even when the surface rotates away from direct sunlight, temperatures barely drop. Night offers no relief. Heat lingers in the lower atmosphere, circulating slowly but never dispersing. The planet becomes locked in a constant state of overheating. This is where the consequences of the earlier collapse become impossible to ignore. The loss of atmospheric balance didn't remove protection. It replaced it with confinement. As pressure increased, the atmosphere became even more effective at trapping energy. Dense gases absorbed infrared radiation more efficiently. Cloud layers reflected some sunlight away, but not enough to matter. What little energy escaped was immediately replaced. Over time, the system reached a new equilibrium. Not a stable one, but a permanent one. Temperatures stopped rising, not because the planet cooled, but because it reached the maximum heat its system could sustain. The surface became hot enough to soften rock. Chemical reactions that rarely occur elsewhere became common. Materials behaved differently under constant pressure and heat. This wasn't a temporary phase. It became the planet's defining condition. The trap was complete. And once a world reaches this point, there is no easy path out. Which means the real question is not why this planet is so hot. It's how many other worlds could end up the same way. This is part of a sequence. Subscribing is how you don't miss what comes next. Extreme heat didn't just change how this planet feels. It changed what the planet is. Once a world enters this state, everything else becomes secondary. Rotation no longer matters. Distance from the star becomes irrelevant. The system stops responding the way planets normally do. What defines this planet now is persistence. Temperatures do not fluctuate in meaningful ways. Day and night blur together. Seasonal variation disappears. The planet exists in a permanent thermal extreme. This matters because planetary heat is not just a surface condition. It affects chemistry. It alters materials. It reshapes the crust itself. Under constant pressure and temperature, reactions occur that would be impossible elsewhere. Rocks soften, minerals behave differently. The surface becomes chemically active in ways that resist cooling. This is not a temporary phase in the planet's history. It is the outcome. The processes that led here no longer need to continue. The system sustains itself. Heat maintains pressure. Pressure maintains the atmosphere. The atmosphere maintains the heat. The planet has crossed into a stable extreme. This is why scientists no longer describe this world as unusual. They describe it as locked. Locked into a state that cannot easily reverse. And this is where the story stops being about a single planet, because the same physics apply elsewhere. Many planets orbit close to their stars. Many rotate slowly. Many lack strong magnetic fields. Some may already be moving towards similar outcomes. This planet shows that habitability is not just about where a world forms. It's about how it evolves. Two planets can start with similar ingredients and end in completely different states. One becomes stable. The other becomes extreme. Not because of a single catastrophe, but because of a sequence of changes that reinforce each other. This is why extreme heat is not the exception. It is a possible endpoint, and once reached, it defines the planet forever. But there is something even more unsettling. Based on everything we know, this planet should never have survived long enough to reach this state. Its formation, its rotation, its atmosphere, and its temperature all point to a system that should have failed much earlier. And yet, it exists, which leads to a much bigger question. In the next video, we'll look at why this planet shouldn't exist at all, and what its survival tells us about how planetary systems really work.